Okay, so in part one, we talked about what is a lateral flow test, how do they work in general, what is the plan for doing it in schools, and let's first look at the probability behind these lateral flow tests. And we looked at this key misconception, which is why not just give two lateral flow tests? Why not? If it's just random, it's just like picking out two names from a hat. It's just like rolling two dice. It's just like picking two balls out of a basket and hoping to get the thing you're looking for. But it is not, because it is absolutely not random. The 60% is not random, and that's what we're going to talk about now. So, Andre, would you like to start by showing us that beautiful viral load diagram, and then you can start talking about viral load?
Yep.
That
So,
seems like a good place to start. And then we can talk about
yeah,
our
yeah.
nice analogies afterwards.
Okay, so what I'm presenting here is some data that a research group has collected, which correlates the various amounts of viral load, and viral load here is referring to how much virus particles are present in the sample matrix that a patient has provided. I assume here it's a nasopharyngeal swab, which is the way we've been conducting these tests since. Yeah, so over here, I'm showing you a histogram that some researchers have found. I should provide the source for this. I'll do it in a sec.
We can also put it in the description. It's okay.
Okay, yeah, but what they found here is the distribution of viral loads for people that are PCR positive for COVID-19, for the SARS-CoV-2 virus. And as you can see here on the y-axis is the frequency, the count, and
That's
what we see
how
on the
many
x-axis.
people, how many cases they found of this many.
Yep. And what you see on the x-axis here is the logarithmic scale for base 10 for the amount of viral load that is being shown in said individual.
And we need to be really careful with log 10 viral load and what log 10 means. Basically, where it says 2, it's actually 10 to the power of 2, so it's 100. Where it says 3, it's actually 10 to the power of 3, 1,000. Where it says 4, it's 10 to the power of 4. So you can see these get very big. 10 to the power of 12, right at the end there, is massive, These logarithmic, when it says logarithmic base 10, it's just 10 to the power of that number.
Yeah, exactly.
We're not going to talk too much about logarithmic scales, but you can still imagine that as the number goes up, the amount of particles you have go up, but actually at each step, they are 10 times more than the step before. There are 10 times more viral particles at number 4 than at number 3.
Yeah, and I think if we give the viewers a nice reference point here at 10 base 6, if I'm not... Oh, sorry.
That's fine. 10 base 6.
Misbehaving. Yeah, if I'm not mistaken... Actually, is this working? Yeah. There we go. If I'm not mistaken, that is a million, 10 to the power 6.
Okay, cool.
Yeah, so if we look at where the black line is on the histogram, that is the reference point for a million. So if people are struggling a little bit working in base 10, everything to the left of that is less than a million. Anything to the right of that is more than a million. But as Nathan says, the numbers increase or decrease very, very rapidly indeed. So the way that the lateral flow device works, it's not the case that it will randomly select 60%. Not select, there's no selection involved, but it will not randomly a certain 60% of users to be positive and 40% to be negative. What 60% sensitivity effectively means in this case is that the test is sensitive enough to detect the top 60% of viral loads that it has been presented with in the past. So where did this number 60% come from? So this 60%, what it says is that it's not inherent of the test per se, but it's inherent of the user. So it doesn't say that if you have COVID, there's a 60% chance it will detect it. What it's saying is that, mistake, I think that's pretty much exactly what it's saying.
That's true.
A bit hard to get the words here correct. I know we were struggling a bit with this yesterday as well. It's basically saying if you have COVID, there is a 60% chance you have sufficient viral load for it to be detected by the test and for the test to tell you have that positive result.
I think, Andre, you should, there's like a way to write text. I think you should write that at the top of the screen. Literally type that out. So I think that's the key thing. That's the sentence we're going to have to keep coming back to. There's a 60% chance that you have enough viral load that the test picks it up.
Yeah, so if we kind of like draw that on this histogram over here, if I draw like an arbitrary line where I'm approximating 60%, sort of roughly on this graph, that's saying that every one of these users here which present the highest viral load have a viral load that is possible for it to be detected by this lateral flow device. Whereas, unfortunately, everyone on the left-hand side here, displayed by the red arrow, even though they are SARS-CoV-2 positive, simply do not have the viral load for it to be detected by this lateral flow device.
Okay. And I mean, we'll keep talking about this. We'll talk about some analogies, but you can see why why that might be an issue, because they still are SARS-CoV-2 positive, but it's not being picked up by the test because the test is not sensitive enough. It doesn't pick up that low amount of viral load.
Exactly. And this becomes a particular problem if we talk about the sensitivity of doing two tests.
Yes.
So in your initial sort of logistic fallacy about running two tests, I believe you're getting 84% sensitivity if the tests were conducted at random. And unfortunately, that is an optimistic number, because that would actually be great if the tests work like that. But it's even worse than you might suspect, because let's say that everyone in this sort of red-hand side of the graph here tested negative for the first test. If you were to conduct the test immediately again, the amount of viral load will not change minute per minute for a person. So we'll talk a bit in the future about how a viral load will change and why it is better to conduct tests over a certain amount of time. But if you could ask someone to run the second lateral flow test immediately, or let's say half an hour to an hour after the first one, if they weren't sensitive enough to be detected in the first one, they are still on the left-hand side of the graph here. So they are not likely to be detected by the second test anyway, regardless of...
So let's imagine our friend Lucas, who has COVID-19. If you want to draw him by the 5. So he is one of these 300 or 240 people. Okay, by the 4. One of the, let's say 250 people, 250 tests that came up with a viral load of 10 to the power of 4. We'll say it's 4 particles, which was not sensitive enough for the test to pick up. He has that many virus particles, but not enough that's not enough for this test to pick up the first time. When you do it again, he's still there. He hasn't magically walked to the other side of the black line. He still has the same amount of viral load. So the test is still not going to pick him up. He's not randomly now on the right-hand side. It's not like he randomly every second could be anywhere in this histogram. He is on the left-hand side of that line, and he is still a minute later on the left-hand side of that line. So the test is still not going to pick him up. So if it was 60% sensitive a minute ago, it's still 60% sensitive now. And it's still 60% sensitive the whole time. The only difference is, where is Lucas on that viral load histogram?
Exactly. There is no randomness in the test. The only randomness comes with the viral load present in the patient. So the probability lies with the patient, not with the test itself.
And that's so interesting and so different to what the test looks. So different. So the probability lies within the patient's own viral load, not with the test itself. The test picks up the top 60% on average. On average, the top 60%.
Yeah.
If you're below that, it will miss you.
Yep. And I know that we might get some questions from some really, really smart people just like interested in this, and I'll try to answer it now. There is a small amount of randomness that we actually picked up on earlier, and that is between the person actually conducting the test. So let's say, because we were getting the number 58 or 60% here from a trained member of the community, but if it was from a trained healthcare professional or a lab scientist, then that number goes up. And that number can be thought of as randomness in a sense. So you will get a slight increase in sensitivity from running a second test, but the numbers will not be anywhere near worth it.
And it's kind of like, basically, me, the self-trained member of the public, is only picking up a certain... There needs to be loads of virus for me to pick up some. Whereas a less trained, like a healthcare professional, will be better at doing the test, so is more likely to find less viral particles. Yeah,
I mean, that number is not very... that number doesn't change much at all, but that number will be enough for that 15 to 20% swing.
Especially because it's an average. It's just, there's lots of people doing it, and they ended up on...
Exactly. There will be some members of the public who can run the test as simply as good as healthcare professionals and lab scientists, but there'll be those who will struggle following instructions or reading the observed readout, which is why you're given an average, which is then used, I don't want to say globally, but in terms of administration of the test.
Okay. So, next thing I think is interesting to talk about. So, I'm going to draw a little graph that is viral load over time.
Yeah.
Now, we're going to assume it looks like a bell curve. We're going to assume it looks like this. And everyone's will be different. Everyone's curve will be different, but there will be a time where it peaks, there'll be a time where it is less. You can imagine this is on your come up, and this is on your come down of your virus. And if we think about our test, let's say our test was accurate only here. This is where it's sensitive enough, where we have 60% of our data here, 40% down here. Now, clearly this visually doesn't quite work, but that's fine. It can only get the top 60%. Now, if I do a test, let's change the color. If I do a test here, so let's say I test here. Here.
Yeah, so you're in the early phase of your infection.
Am I going to get it? Is it going to show up on the test? Probably not, because the test only picks up information here. A minute later, I'm still there. So even if I test there, it's not going to work. But 3 days later, I might now be here. 3 days later. Because my virus has developed. 3 days later, I might be there. And actually, if now, will I get a positive test? Yeah.
Yeah, exactly.
Now I will get a positive test. Which is why it is important. One negative doesn't mean you don't have it at all. It could just mean you are at either of these steps. You are on the come up of your viral load or on the come down of your viral load. And that's why, look, if you get a test here and it's negative, and then so this is day 1, and then 3 days later you're here and it's still negative, well, that's good. It means you are either don't have it at all or on the come down, which is good. But the key thing is that the 60% sensitivity captures you at your most infectious as well. Your most infectious.
Yeah, I mean, obviously the peak will be covered by the highest viral load, and in every single case, that's just definition of.
Yeah, and it could be. I mean, you could look like this. You could look like this. It could take you ages to get here, and then could look like this. But either way, if the test is only capturing you, telling you're positive at the top 60%, and remember the test goes up to 78%, it's just human error that it's down to 60 with general members of the public. If you test it here, but then you straight away test it here, you still have the same viral load, so it's not going to come up positive. It's not random. You're not randomly here once and randomly here next and randomly here next and randomly here next and randomly here next.
Yeah, exactly, which is why there's very little point in running the same test twice, and it's more useful, as the government suggested, to run them several days apart, at least 3 days.
Okay, so a couple of things I think are important to talk about. One is let's just quickly finish up all the things that were wrong with this, and then I want to talk about does lower viral load mean lower infectiousness? Are the kids that are asymptomatic, what's their viral load going to look like? Those are the two things I want to talk about. So, so this slide is wrong. It's wrong. Because 2 lateral flow tests we've just seen do not work like this. It is not 60% random balls in a bag. It is, do you have enough viral load for it to pick it up? If you didn't have it before, you're not going to have it a minute later.
Exactly. If the probability lied with the test, then the maths here would completely check out.
But it doesn't.
The probability lies with the patient itself.
Good. So everything, and I'm going to link the video as well, everything from this minute on is basically wrong. But believable. Talk about mass testing being better than no testing. We talk about the idea that if you have a positive test, you don't need... You know what? None of this is true, so it doesn't matter. But the key thing is... what we're thinking about, where if you have a positive test, you don't need to retest it, is because if it's so specific that if you get a positive, it's definitely positive, then you don't need to retest it, because we know it's positive.
Agreed.
But also relevant, because not true. Key things, though, and I think, does this still stand, Andre? Because the key thing here is that, what if I get a negative test result? Well, for 100 people with COVID, there could there could still be 40% of people, and it's not because the test is random, it's because these 40% of people have a viral load less than needed.
Yeah, exactly. So if anything, the numbers are even more skewed towards being more careful here because for this test, 40% of people who have COVID, because fundamentally we don't know how many people taking a test will have COVID. Like if we say 100 students, it could be anywhere between 0 and 100 of them displaying COVID.
We hope it's not 100.
Yeah, if all of them are negative, there is a small but very real possibility that none of them had COVID to begin with. In which case,
so they could have it could be a graph like
restrictions.
this, where they all have viral load below this 60% threshold. They all have viral load below there.
Yeah, but I think in this case, you're suggesting that they have COVID. They just don't display enough viral load for it to be detected by the test. But what if fundamentally none of them have any viral load whatsoever? Oh, yeah. Because simply no one has COVID.
Yeah.
Yeah. Unfortunately, we can never know this unless everyone was PCR tested. Because the sensitivity of PCR tests goes down to very close to 100, and you can detect viral loads a tiny, minuscule amount.
So that if we're looking at our viral load thing like this, our viral load over time, so let's say the lateral flow picks up this.
Yep.
The PCR picks up everything. Pretty much everything.
Yeah, or close to everything.
Oh, and is that why with a PCR test, it could tell you're positive, but actually you have barely any viral load whatsoever?
Yeah, but you still need COVID to get that viral load.
Yeah, so you still have COVID.
PCR detects it detects the genetic information of COVID in your system.
Okay, and so the key thing is still that it's so important that people continue to follow guidelines. In particular, in those 3 days between test results, in those 3 days, or not test results, but if you're doing 3 tests apart, and on day 1 you're here, and on day 3 you're here, between here, you are still infectious. Even though you couldn't be caught before, now you can be caught. Yeah. So important that no matter what your test says, act like, I could still have COVID, so I don't want to give people COVID.
Yeah, completely. You'll be in a false sense of security if you get a negative test and you're acting like you don't have COVID, especially if you are only on 1 negative test.
Yeah.
If you take the second negative test 3 to 5 days afterwards and you get a second negative, you can be a bit more relaxed that you are not carrying the virus. Obviously, you can still absolutely be doing so if you just simply don't display the viral loads enough for it to be detected by the test. And this is something we see typically with asymptomatic people, where the severity of symptoms is quite intrinsically correlated with the amount of viral load that is present in a patient.
Okay, yeah, so that's the key thing. The people, do you want to get your histogram up again?
Yep.
The people on the left-hand side of that histogram with lower viral loads are more likely to be asymptomatic, and are more likely to, and so our students who are more likely to be asymptomatic our students are more likely to be like Lucas and more likely to be on the left-hand side of that thing. So our students are more likely to have negative COVID tests even though they do have COVID. Because they're more likely to have a lower viral load. Now, we don't know at what part of their journey they are. We don't know if actually they're never ever gonna breach that 60%. Or if they're just about to, we don't know. But the key thing is, we are more likely to get lower viral loads in our asymptomatic cases.
Yeah, as a general rule, that is the case. I mean, there is a huge amount of variability, but it's something that we can as a general rule, we can definitely approximate that. Especially those that are symptomatic display a huge amount of viral load in the samples that they'll be presenting to these tests.
Okay, very interesting. What infectiousness? So someone could say, well, look, we're missing Lucas over here on 4,000 not 4,000 on 10,000 10 to the 4 on 10,000 viral load particles, but it's not that bad because he's 10 times less infectious or 100 times less infectious than the 1,000,000 person. Is that true?
No. He will be less infectious, but putting a hard number to it would be a huge amount of guesswork and will just fundamentally be wrong.
Why would he be less infectious?
Well, there's a lot of factors that go into how infectious someone is. The first one being, are they displaying symptoms at all? You can still be on this low viral load part of the histogram and still display symptoms. You could be on the high part of the viral load diagram. You could be somewhere up here and be very luckily not displaying any symptoms. If someone is coughing and sneezing, naturally they are less infectious. I'm sorry, they are more infectious.
Because
they have
they're more
way
chance
roots.
of more routes of infectiousness. Yeah.
Exactly. There's much more pathways they're presenting. They're, for lack of a better term, polluting the air around them with viral particles that can be picked up by people next to them, or just it can hang in the air. I mean, there have been cases and studies, case studies of those, especially those in South Korea, where they've detected people picking up samples up to 6 meters away from people who have been infected with COVID. And this could be to like circulation in the air. Obviously, if you're in a well-ventilated room, this infectiousness goes down. If you're in a room that has a lot of recycled air, which I imagine might happen quite a bit in school with air conditioning or ventilation systems that don't
Schools that don't have
ventilate,
windows. Classrooms that don't have windows that work.
especially in the winter as well, you won't be having that window open for too long.
Yeah. Well, we
Yeah.
have all our windows open and everyone just wears coats all the
Yeah.
time, and it's just what life
Yeah.
is.
So saying that, if you are on the lower end of the distribution that, like Lucas is here, you are likely to be less infectious. This does not mean that you will not be infectious at all. I want you to take that less infectious with a pinch of salt, because
You're still infectious.
fundamentally, he's still infectious. Every breath he takes, he will be releasing droplets, which could be picked up by other people. Any exchange of bodily fluids in school activities will
We don't
transmit
exchange that many body fluids in school activities. Just want to throw that out there.
between students.
Between students. Yeah, exactly.
I mean, fundamentally, the students wouldn't. I mean, they don't want to collect the virus at all, because they become easily transmissible to their home bubble as well. But the virus also, even in asymptomatic cases, that does seem to have some long-term health detriments that we don't want to be dealing with.
Okay. So, some key takeaways, and I'm gonna write these up on a PowerPoint slide. Key, very important takeaways. So, firstly, sensitivity is not random. It's not random.
Yeah.
We can say based on your viral load. Based on your viral load. So you could have there's a random chance of what viral load you have, but if you have that viral load, it's going to show up.
Yeah, I mean, to an extent, there's a random chance what viral load you have. You can't have an infinite number of viruses in your system.
That is also true.
But let's just say between a positive and between a minimum and maximum based on the histogram I've shown, that I believe is data taken from, I believe it was around 3,000 samples. I mean,
yeah, I think I saw that.
It's irrelevant. It's enough that it's given a good distribution of what we can expect to be the bottom and top of the cumulative curve.
Okay.
For viral loads.
Yeah. We can. So go on.
So let's say that the amounts that you get again is not random, but sits in that distribution. And obviously, the probability of sitting on the peak of that distribution is higher than you sitting on.
There are more people at that peak than at the other bits.
Exactly.
Yeah.
And therefore, you are more likely to sit at that peak if you have COVID.
Yeah. Next thing to say is that asymptomatic. This seems to asymptomatic cases are generally more likely to have lower viral load, which is harder to detect.
Mm-hmm. Yeah, 100%.
So generally that is the case. Asymptomatic, but they are less likely, perhaps, to be as infectious. But still, asymptomatic cases are generally more likely to have a lower viral load, which is harder to detect. If the test says you have COVID, you do. You have. You basically do.
Well, that is judged by the specificity, and we can say that there is a 99.64%. I believe that was the specificity of it. Chance that you do have COVID. Basically, if you have the positive COVID test, take it as real.
Yeah. As truth. The other thing that's important, if I get a negative test next week, if I get a negative, don't trust it. Don't take it as gospel unless you've had a second negative 3 days later.
Yeah, and even then, like with us understanding how it works,
Yeah.
you shouldn't be taking it as gospel. You should absolutely be taking it that you are not in that sort of phase of the viral infection that you will be a huge risk factor. But saying that you don't have COVID even after 2 negative tests is making an assumption.
Yeah.
It's still making an assumption.
Yeah. 2 tests 3 to 5 days apart, and that's why the government says that. Gives 2 tests 3 days apart gives your body a chance to have changed your viral load. 2 negative tests are more likely to mean you don't have COVID. Oh, 10 minutes left. That's cool. You don't have COVID, but still be safe. So still be safe. You could just have COVID and just not have enough things, not have enough lateral flow event. Anything else? Any other key takeaways?
Well, just I don't think there's any more key takeaways from what we've discussed. I think there's a couple more points that we could touch on. These numbers that we're getting for this lateral flow test is just the one that you've been provided with. Every lateral flow device will have different sensitivities because they all use slightly different technologies, such as different reporter probes. They're detecting different parts of the protein. There could even be potentially lateral flow devices that work on the detection of more than one protein, viral proteins. So there's nothing inherently stopping a lateral flow device from having 2 test strips, where one detects a spike and one detects another protein on the virus, say the nucleocapsid.
Oh, that's interesting.
Yeah, and in that sense, I think your initial analogy of probability becomes more applicable. I wouldn't say it's still perfect, but it becomes more applicable. Let's say there's a 60% chance that it detects one virus and a 60% chance it detects another virus, then the sensitivity of the assay does in fact increase in that sense.
Yeah, that makes sense.
But it's still intrinsically linked to viral load, so let's not get into that.
Not random.
That's quite complicated. Yeah.
Okay. There are some bonus thoughts I want to talk about. Thank you so much, Dr. Shamsabadi. It's been an absolute joy to talk to you. It's been super interesting. I've learned so much. I feel so much wiser. I also feel like, when we're going to talk about this in the bonus thoughts, oh my god, it's easy to create COVID misinformation just because... How are you meant to know this? Like, when you see 60% and they don't explain what that means, why would you not think, oh, it's just randomness? Why would you not think that 60% means 40% of the time it's just wrong?
Yeah, and you're doing it unintentionally. You're battling everyone who's creating COVID information intentionally to...
Exactly.
That we are seeing in the world today anyway, so...
Exactly. So, wait around... So, people that are watching, if you are still watching, thank you, we will have a bonus video where we talk about some extra things like how easy it is to have COVID disinformation, what other interesting thoughts we have about this. But for now, thank you so much, Andre. I love you a lot. You're a legend. And I'm so excited.
It's been an absolute pleasure.
It has. So see you in the next one.
Yep, thanks for listening.